Chapter 4, Section 3, Patterns and Nonlinear Functions. Linear and nonlinear functions. A linear function has a graph that is a non-vertical line, which means it's a line that is not going straight up and down, or part of a non-vertical line. And a nonlinear function is a graph that is not a line or part of a line. When I'm saying line, a line means a straight line. Like you could take a ruler and it would fit up to a ruler and it would be a straight line. So a linear function is going to have a graph that is a straight line that is not vertical. And a nonlinear function is going to have some sort of curve in it. So it is not going to be a straight line. If you look at these graphs, it's asking you, is this a linear or a nonlinear function? If you look at the first graph in the top left, that would be a nonlinear function. It is not a straight line. The next one would again be a nonlinear function because it is not a straight line. The third one on the top would be a linear function. It is a straight line. So we have two nonlinears and then a linear. If you notice, the difference is the first two have some sort of curve to them. The third one is a straight line. Again, the next one on the bottom left is going to be a linear function again, and that is actually a horizontal line. Some people say it's a zero slope. We haven't gotten into slope yet, though. So it is a linear because it is a horizontal straight line. There's no curve in it. The next one is nonlinear. If you notice, it kind of curves there on the x-axis. And then the last one is, again, a nonlinear because it does have a curve to it. So linear versus nonlinear lines. Linear are going to be straight lines. A nonlinear is going to be a graph that has some sort of curve to it. A linear or nonlinear function from a table. It says if a function is linear, the x value will increase or decrease at a constant rate, and the y value will increase or decrease at a constant rate. Now, the constant rate of the x and the y values do not have to increase or decrease at the same rate, but the x values need to be increasing or decreasing at their own rate, that is constant, and the y values need to be increasing or decreasing at their own rate, that is constant. If you look at these examples, we are given x and y ordered pairs. If you look across the top, every time we're looking at the top left one, the 0, 5, 10, 15 for the x's, the pattern for the zeros is each time I am adding 5, so 0 plus 5 is 5, 5 plus 5 is 10, and 10 plus 5 is 15. And if you look at the y values, to go from 20 to 16, I'm subtracting 4, and the pattern works all the way across this table. So we could say because x has a constant increase and y has a constant decrease, we can say that this would be a linear function. Now, if you look at the next example, to go from 0 to 2 in the x's, we add 2. From 2 to 4, we add 2, and from 4 to 6, we add 2. So my x values have a constant increase of 2. If you look at the y values, though, to go from 0 to 2, I add 2. To go from 2 to 8, I add 6. To go from 8 to 18, I add 10. That is not a constant rate because I'm adding a different value each time. So this would be a nonlinear function. And the last table, my x's are increasing by 1. My y's increase from 1 to 3 is 2. From 3 to 6 would be plus 3. And from 6 to 10 would be plus 4. My x's, again, have a constant rate, a constant increase. But my y's do not have a constant increase. Each time that I move to the next y value, I'm adding a different number. So this would, again, be a nonlinear function. The first example says the number of centimeters is a function of the number of inches as shown in the table. Is the function linear or nonlinear? You can always plot these points and connect them and see if they would make a straight line or if it would be a curved line, but since I have these decimals, that's not going to be very easy to graph. But we can look at the relationship between the inches and the centimeters and see if they are increasing or decreasing at the same rate in the table to say that they are either linear or nonlinear. If you look at the inches first, each time I go down the column for inches, I'm adding 1. The next one might be a little bit more difficult to see, but each time that you are going from like 2.54 to 5.08, you're adding 2.54, and that same thing is happening each time I move down the centimeters column. So I have a constant rate of adding 2.54 to centimeters. I have a constant rate of adding 1 to the inches, which means that this function would be a linear function. This next example says the table shows the number of calls made in a phone tree during each level. Identify the pattern to complete the table. How can you represent the relationship using words, an equation, and a graph? If you look to go from 1 to 2, and 2 to 4, and 3 to 8, those are my corresponding x and y values. You're asking yourself, first of all, ask if this is a linear function. My x's are increasing by 1 each time. But if you look at 2, 4, and 8, to go from 2 to 4, I'm adding 2, 4 to 8, I'm adding 4. So this is not going to be a linear function. And I'm going to tell you this right now. When you're working on this assignment, you need to think about exponents. Now, you can have a variable that is an exponent, so you could have like 3 to the power of x, or you can have x to some power, so you could have x squared, x cubed. Anytime we have a function that is a nonlinear function, we might start trying to think of exponents. Because this is a nonlinear function, I'm not going to be able to just add the same value to x repeatedly or multiply the same value by x repeatedly. So like adding 1 to each x value isn't going to work. Even though 1 plus 1 is 2, 2 plus 1 is 3, so that pattern won't work. If you look at the y values, we have 2, 4, 8. If you think about your powers of 2, 2 to the first power is just 2. 2 to the second power is 2 squared, which is 2 times 2, which is 4. 2 to cubed, or 2 to the third power, is 2 times 2 times 2, which is 8. If you were following along in the y column, you can see that 2, 4, and 8 are my first 3 values. So that is my pattern. Y is 2 to the power of x is how I would say it using words. Written in an equation, it would be y equals 2, and then my exponent would be x, because it depends, that's going to be my input. That's where I'm going to put, like for instance, I'm going to plug in 4. So 2 to the fourth power means 2 times 2 times 2 times 2. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So the ordered pair for x would, for when x equals 4, would be 4, 16. And 2 to the fifth power, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So my ordered pair for when x is 5 would be 532. Again, to find the patterns for x's and y's, or inputs to outputs, it's going to be a guess and check process. You want to try to find a pattern, and that will help you to hopefully have some ideas on what a good guess might be. But really, finding a pattern from a table is a guess and check type problem. So if you think you have the right answer and it doesn't work out, don't get discouraged. Try to find another pattern that you can use. Always start with one ordered pair. Always start with like the first one and say, what can I do to 1 to get 2? And keep trying to think of different ways that you could go from 1 to 2, and that's going to be helpful. Sometimes you might get stuck. It's okay to go to the next problem and try to come back to it. Sometimes you just need to take a break, and when you get back to it, it clicks and you get it. But just don't get discouraged. This is going to just be the best thing that I can tell you is just guess and check. To graph these ordered pairs on a coordinate plane, notice that this is not a linear function, which I had already decided because my x and my y's didn't have a constant pattern. And this is how you would graph these ordered pairs and connect them. The next example says the ordered pairs 1, 1, 2, 8, 3, 27, 4, 64, and 5, 125 represent a function. What is a rule that represents this function? I personally think it's always easier to look at patterns for ordered pairs if you put them in a T-chart or a table. So I'm just going to take these ordered pairs that they gave me and I'm going to write them in a table. Notice my corresponding X and Y's would form the ordered pairs that I was given. It's easy to ask yourself now, first of all, is this a linear function? And the answer is no, because I'm going from 1 to 8, 8 to 27, 27 to 64. I can't add or subtract the same thing to get these numbers. So again, I'm trying to think exponents. What can you do to 1 to get 1 that has an exponent? What can you do to 2 to get 8 that has an exponent? If you think of, well, 1 squared is 1, right? But if you go down and you do 2 squared is 4. What about 1 cubed? Think about 1 cubed is 1 times 1 times 1. Well, 1 times 1 is 1 times 1 is 1, so that does work. Think about 2 cubed. You have 2 times 2 is 4 times 2 is 8. That did work, so let's try the next one. 3 cubed. 3 times 3 is 9 times 3 is 27. That one worked. Go down and make sure the last two work. 4 times 4 is 16. 16 times 4 is 64. And then the last one, 5 times 5 is 25, times 5 is 125. So I did find the rule. It is y equals x cubed. Today's assignment is on page 266. It's numbers 1 through 12, number 17, and then 20 through 26.